The goal of this video will be to solve a few problems using mathematical induction. And let's start with the first one. So we have to prove 1 times 2 times 3 plus 2 times 3 times 4 all the way up to n times n plus 1 times n plus 2 is equal to 1 over 4 n times n plus 1 times n plus 2 times n plus 3. Now, the base case for n equals 1, that is sorted out. The first term here is just 1 times 2 times 3. And the right-hand side, well, that is equal to 1 over 4 times 1 times 1 plus 1 times 1 plus 2 times 1 plus 3, which surely is just equal to 6. On both sides, you have the same thing. Now, let's talk about the inductive case, the case wherein you need to prove that if P, the statement P of n, let's say, we need to prove that if P of k holds, that implies P of k plus 1. So P of k plus 1, the left-hand side in that statement would be 1 times 2 times 3 plus 2 times 3 times 4 dot 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 times k plus 1 times k plus 2. This is from P of k. We know that we have assumed this to be equal to 1 over 4 times k plus 1 times k plus 2 times k plus 3. Now, when we transition towards proving P of k plus 1, we just need to add one term right here. So we need to add k plus 1 times k plus 2 times k plus 3. And since we are adding this to the left-hand side, we also add this to the right-hand side. So we do this, sorry, k plus 1, k plus 2 times k plus 3. Now, this thing, left-hand side, is what we need to get in order to prove P of k plus 1. We now simplify this part. So if you look carefully, this part is common, so you can write that common. So k plus 1 times k plus 2 times k plus 3 times 1 over 4k plus 1. And now simply you can just write this part as k plus 4 over 4. The other three terms, just write them as they are. And this finally gives you what you required. This gives you 1 over 4 k plus 1 times k plus 2 times k plus 3 times k plus 4. And, well, we have proved the inductive hypotheses. The base case was already done, hence this statement holds true. Let's move on to the next problem. The next problem has fractions in it. So again, the base case is pretty simple. The base case, just put n equals 1. So the left-hand side will be 1 over 3 times 7, that's 1 over 21. And the right-hand side will be 1 over 3 times 4 times 1 plus 3. That's also 1 over 3 times 7. That's also equal to 1 over 21. So the base case is done. We did it using n equals 1. Let's now prove the inductive hypothesis. So inductive case. Now, in this, we assume that for some k, P of k holds, and then we need to prove from that P of k plus 1 also holds. So P of k would mean 1 over 3 times 7 plus 1 over 7 times 11, all the way up to 1 over 4 times k minus 1 times 4 times k plus 3. This is equal to k over 3 times 4k plus 3. We assume that this is true. Now, in order to prove P of k plus 1, we just add another term, and that other term is 1 over 4k plus 3 times 4k plus 7. Instead of k here, you just put k plus 1, and that gives you this term. Let me erase this. And since you added this on the left hand side, you also add this to the right hand side. So this gives you 1 over 4k plus 3 times 4k plus 7. The left hand side, again, as before, is sorted out. On the right hand side, well, you take 1 over 4k plus 3 common out, and you will have k over 3 plus 1 over 4k plus 7. And 1 over 4k plus 3. Again, this is just simple algebra. This is going to lead us to 4k plus 7 times k plus 3 divided by 3 times 4k plus 7. This does get a bit messy here, since now you have a quadratic. Let me write that quadratic here. So 4k plus 3 times, and here in the denominator you have 3 times 4k plus 7. This will be 4k squared plus 7k plus 3. And now we need to factorize it. So if you went on to complete the square, that's one way to do this. The other way is you can observe that this can be written as 4k plus 3 times 4k plus 1. And once you do that, 4k plus 3's would get cancelled out, and you will have k plus 1 divided by 3 times 4k plus 7. And if you compare this with what we had for k, this is exactly what we wanted to get. If you put k if you replace k by k plus 1 all in both the numerator and the denominator, you will get this. So p of k plus 1 holds true when p of k holds true.